Let's begin with the big idea behind the Bolzano Weierstrass theorem. Take any sequence of numbers that is bounded, meaning it never wanders off to infinity in either direction. The theorem says that even if the sequence itself never settles down or converges, it always has a smaller subsequence hidden inside it that does converge. To prove this properly, we start with the first principles proof, using a method called repeated bisection. Since the sequence is bounded, every term lies inside some closed interval, say from a lower bound to an upper bound. Because there are infinitely many terms in the sequence, but only one interval, this interval must contain infinitely many of the terms. Now we cut this interval exactly in half into a left half and a right half. Since the whole interval contained infinitely many terms, at least one of these two halves must also contain infinitely many terms. We choose that half, whichever one it is, and throw away the other half completely. We repeat this process forever, each time splitting the current interval in half and always keeping the half that still contains infinitely many terms. This produces a sequence of nested intervals, each one sitting inside the last, and each one exactly half the width of the one before. Because the width keeps halving forever, these interval widths shrink down towards zero. From each of these shrinking intervals, we pick out one single term of the original sequence that lies inside it. This gives us a new subsequence built from the original sequence, one chosen term per interval. Since the intervals containing these chosen terms are shrinking towards a single point, the chosen terms themselves must be getting closer and closer together, so this subsequence converges. As a check, notice that at every stage we only ever discarded intervals that had merely finitely many terms left in them, so we never accidentally threw away the possibility of continuing forever. This confirms the bisection process is valid at every single step, and so the subsequence it produces really does converge. That completes the first principles proof using bisection. Now let us look at a genuinely different proof of the very same result, using an idea called peaks, which does not rely on splitting intervals at all. Call a term of the sequence a peak if every single later term in the sequence is strictly smaller than it. In other words, a peak term stands taller than everything that comes after it, forever. There are only two possibilities for how many peaks a sequence can have, and we treat each one in turn. Suppose first that there are infinitely many peak terms in the sequence. By definition, each peak is smaller than the peak before it, since every later term must be smaller than an earlier peak, so this gives us a decreasing subsequence. Since the original sequence was bounded, this decreasing subsequence is also bounded, and a bounded decreasing sequence must always converge downward to some limit. Now suppose instead that there are only finitely many peaks in total. Then after the last peak, every term that follows is not a peak, which means for each of these later terms, there is always some even later term that is bigger than it. We use this fact repeatedly to build a subsequence where each chosen term is bigger than the one before it, giving us an increasing subsequence. Since the original sequence was bounded above, this increasing subsequence is also bounded, and a bounded increasing sequence must always converge upward to some limit. So in either case, whether there are infinitely many peaks or only finitely many, we always end up with a monotone bounded subsequence, and such a subsequence always converges. As a check, notice both cases together cover every possible sequence completely, since the number of peaks is either infinite or finite, with no other option, so the proof leaves no gaps. This peak proof is genuinely different from the bisection proof, because it never touches the interval or its width at all. Instead, it organizes the sequence itself by comparing terms directly to build monotonic order. Finally, let us check why the boundedness condition in the theorem is actually necessary. Consider the sequence of natural numbers, 1, 2, 3, 4, and so on forever, which is not bounded since it grows without limit. Any subsequence taken from this sequence also grows without limit, so no subsequence of it can ever settle down and converge to a finite value. This shows that without the boundedness assumption, the theorem completely fails, confirming that boundedness truly is essential for the result to hold.